In this lecture, we are going to learn about Aloha, which is a multiple access protocol, and it's one of the simplest one to understand what is multiple access. So here, what we say is that there is a medium, okay, there is a shared medium. Let's say there is a Ethernet wire, and there are station 1, 2, 3 and 4. Okay, 4 stations are there who can transmit. They have to transmit their frames. Now there are a few constraints. The constraints are that when someone is transmitting its frame, others should not transmit their frame, okay, because if two people simultaneously transmit their frame, then there will be collision, okay. So there is chance of collision, okay, there will be collision. And then, so they should not be transmitting at the same time. Even if one of the bits get collide, then also it will be collision, okay. So multiple access, let's try to see what is pure Aloha. So 4 stations are there. This is the timeline, okay. So frame are a group of bits, okay. So there are a bunch of bits, let's say 1000 bits. So we need to, it will take some time to send the frame across the wire, okay, so that it is sent from one part of the Ethernet to the other end of the Ethernet, okay, and that takes time. So what happens is that if this frame starts here, it will come here, then it will travel like this, and finally it will come here, okay. So it takes some time, and while this is traveling, okay, none of the other frame should come and collide with it, because both of them will get garbled, okay. So this frame, this time frame, okay, none of the other stations were transmitting, so this frame is successfully transmitted. Then let's see, frame 3.1 is the next frame that is transmitted by station A. So this is perfectly working fine till here, but after that it finds that while this frame is still being transmitted, frame 2.1 by station 2 starts getting transmitted. So these two will now collide, and then what happens, some part of it, while it will go without any collision, so but it will now collide with frame 4.1. so here some collision takes place between these two, then between these also frame 1.2. so all the 4 frames will get corrupted, okay, and none of them will be successful. So even when one of your bits collide, then there will be collision and whole frame will be corrupted. Now let's see about this frame. So frame station 2 again transmits the second frame, but it again collides with frame 2 of station 4 because they are overlapping in time, okay. So only a frame will be successful if it is not colliding with any other one. So frame 3.2, so station 3, this frame is okay because none of the other people are sending in this particular time slot. So you can see that 1 and 2, just 2 frames succeeded, and 1, 2, 3, 4 and 5, 6 frames got corrupted, okay, because of collision. So the efficiency is just 6 by in fact 1 minus 6 by 8. So it is 1 by 4th of a packet, or only 25% are getting successfully transmitted, okay. So this is the problem with a shared medium, okay, where anyone is transmitting whenever they have some data to transmit, okay. So in fact you can now imagine that if you are going to increase the number of hosts, the collision will increase and the throughput or the number of successful transmissions will become less, okay. So this is the simple Aloha algorithm. So we will just look at it in here, okay. So this is the procedure for pure Aloha. So I am a station, okay. So station, it finds that okay, it has some data to send, so it will put its counter k is equal to 0, which means this is my first attempt. Okay, so k represents here the number of attempts. So now what happens is that it will start sending its frame. Okay, so the station transmits its frame, and then what will happen is that I am station A, I am sending to station B. So I will transmit, and how will I know that okay, I have succeeded? So B will send me an ACK. So if TP is the maximum propagation time, which is the maximum propagation delay that it will take for one frame to be sent to the other side. So now I know that okay, in twice TP my ACK should be here. Okay, so what happens is if ACK is received, yes, my transmission was successful. But if ACK was not received, so what happens is that I will say that okay, I'm now incrementing my attempt, saying that okay, my first attempt failed, let's try out the next time, second one. If second attempts fail, then I will put k is equal to 3. But you can only try till a maximum of k max, which is normally set to 15. So if you are unlucky and you are failing many times, and if it exceeds 15, so you should abort your transmission. But if your number of attempts is less than 15, so what we do? We choose a random number r, which is between 0 and 2 to the power of k minus 1, where k is your number of attempts. So if I have tried out, let's say 3 times, then this is my third trial, then what I will do? I will generate a random number from 0 to 7. Okay, and then any number that I get, let's say r, so I will wait, my waiting time will be r into TP or r into TFR. What is TP? The maximum propagation delay. So I will wait, let's say I got a random number 4, so I will wait for 4 into propagation delay time, or I will wait 4 into TFR times, where TFR is the average transmission time. Okay, so I somehow wait some random amount of time. And how does this randomness help? So let's say there were 2 stations, A, B, and in fact add third one. Now let's say all of them are trying and they have failed, k is equal to 4 for them. So now let's say they were simultaneously transmitting, but so all of them failed. Next time they will all choose a random number from 0 to 15. So let's say A chose 7, B chose 10, and C chose 2. So now what will happen? This will wait for the least amount of time and it will now transmit. Then this will transmit, then this will. So now there is lesser probability that all of them will be now sending at the same time, because of this random amount of time for which I am waiting. Okay, so this randomness helps in removing the collision. So let's try to solve a few numericals that will make our concept more clear. So there is a station. The stations on a wireless Aloha network are a maximum of 600 kilometer apart. Okay, so there is a wireless Aloha, okay, and they are maximum 600 kilometer apart, the stations. If we assume that the signals propagate at 3 into 10 to the power of 8 meters per second, okay, speed of light, then what we can say, the 2 stations that are farthest apart are 600 kilometer, and the light travels at this speed. So what will be the propagation time? It will be 600 into 10 to the power of 3 meters by 3 into 10 to the power of 8 meters per second. Okay, which comes out to be 2 into 10 to the power of 5 divided by 10 to the power of 8, so which is 2 millisecond. So this is the propagation time. Okay, so now it says that okay, what will be the, now we can find the value of back off time. Okay, so usually the back off time, we randomly choose a number from 2 to the power of k minus 1, so 0 to 2 to the power of k minus 1, and then we multiply it with TFR or TR. So for k is equal to 1, so you have range 0 to 2 to the power of 1 minus 1, so 2 minus 1, which is 0 or 1. So in that case, stations need to generate random number with value 0 or 1, and then they will either wait for 0 TB or 2 milliseconds, okay, because TB here is 2 milliseconds. But what happens if your k is equal to 2? Then I have values from 0 to 2 to the power of 2 minus 1, which is 0, 1, 2 and 3. So this means that TB can be either 0 or 2 millisecond, 4 millisecond or 6 milliseconds. So if your random number was 3, so you will wait 2 into 3, which is 6 millisecond. If our attempts was 3, so we will wait from 0 to 7. R will be from 0 to 7, and then we will be waiting either 0 to 4 till 14, okay, seconds, milliseconds. And when k is usually greater than 10, we set k is equal to 10, okay. So this is there. Now what is the vulnerable time for pure Aloha, okay, and what is this period where I am susceptible to collision? So let's say I am station A, I begin at this time t, and my transmission time is TFR. So I'm going to be starting at t, I will be transmitting till t plus TFR. So I can have collision if someone had started earlier, okay, at this time. If someone had started earlier than this, so there would have been no collision, because maximum it is TFR is the length. But if someone started after the time t minus TFR, then there will be collision, because your frame length is equal to TFR. So here it started, then it will collide with my beginning. In the end also, if someone starts here in this period between t to t plus TFR, then also there will be collision. So this time interval, in this time interval, there should be no other stations transmitting. So it will be twice into TF of FR, okay. That's there to know this is the vulnerable time. Now let's try to see. So they are calculating now TFR. So always you have a concrete example, it helps. So there is a pure Aloha network that transmits 200 bits frame. So length of the frame is 200 bits on a shared channel of 200 kbps. So I transmit at the rate of 200 kilobits per second. So what will be the time taken for bit transmission? 200 into 10 to the power of 3 bits per second, okay. So it will be 1 millisecond, okay. So the vulnerable time then becomes, so this is TFR is 1 millisecond, so your vulnerable time will be twice of that, so 2 millisecond. So no station should be starting when our station is starting, and the time period for transmission is 1 millisecond. So no station should have started 1 millisecond before our transmission, less than 1 millisecond before our transmission, and between this period, okay. So that's the case. And let's talk about throughput. How efficient is this one? So efficient means if I'm sending 100 packets, frames, how many of them are really going to be transmitted? That is, they are not being affected by collision. So that throughput is given by S is G into e to the power of minus 2g. What is G, you will ask? So G is average number of frames that are sent in 1 TFR, okay. So in one frame time, what you send, the average number of frames. So this has a throughput that is maximum itself is just 18.4%, okay, and that happens when you have average transmission rate of G is equal to half frame per second, okay. So let's try to see one more problem. So a pure Aloha network transmits 200 bits frame on a shared channel 200 kbps. So again, from last calculation, our frame transmission time TFR will be 1 millisecond. What is the throughput of this system? All stations together produces if 1000 frames per second are sent. So if 1000 frames per second are sent, it means one frame are sent in 1 millisecond time. So your G is equal to 1 frame per time of the frame unit. Okay, G is 1 here, so your S is G into e to the power of minus 2G. So if you do the calculation, it comes out to be 13.5%. And then it asks, what is if I am sending 500 frames? So it means 500 frames per second. Okay, so 500 frames per second, or this is 500 by 1000 frames per millisecond. Okay, which is half frame per millisecond, or in the TFR time period. So G will be now the best case, and it will be, if you see, so it is 18.4%. okay, so this shows how you calculate the throughput, and best throughput is this. If you try to decrease the number of frames per second, then also it's going to be 15.2%. okay, so that's the case for pure Aloha. And pure Aloha, we can very much improve it. Why? Because we never took care of, okay, so there was a very big that contention window, okay, kind of vulnerable time. So here what we do, we make slots. Okay, I know that one frame takes TFR time, so I will make slots of that length. And then there is a rule that stations can transmit only at the starting time of the slot. So frame 1.1 got transmitted, there was no collision. Frame 2.1 started, but frame 3.1 also started. Okay, so frame 2, station 2 and station 3 both sent at the same time, so there was collision. During the third time slot, against frame station 1 and station 4 sends packets together, so there is collision here. In fourth slot, only station 2 sends, this works fine. In fifth slot, only station 4 sends, it works fine. Okay, so now you can see our vulnerable period has decreased. So now there will be no chance that, okay, any previous frame that was sent, it will collide with a new starting frame. Only now our vulnerable time is just one frame slot, one TFR. Okay, so that helps in improving the throughput. Okay, so the improvement is now S is G into e to the power of minus G, and here your maximum throughput will be when you have only one frame per time slot you send. So you have 36.8% is the throughput. Okay, that means out of 100 packets, if you send, 36.8 packets will be transmitted successfully. And vulnerable time is just 1 times TFR. Okay,